An interstellar object just lost 13% of its mass. That's billions of tons of material, gone in weeks. But here's what makes absolutely no sense. The tail that should have appeared barely did. We're not talking about a faint tail or a small tail. We're talking about a tail so subdued, so far below expectations that multiple observation teams initially reported it as absent. We're talking about an amount of mass so staggering that when comets lose even a fraction of this much material, they light up the sky with tails stretching millions of kilometres. Yet on November 5th, 2025, when telescopes turned toward 3i Atlas after its closest approach to the Sun, they saw something that shouldn't behave this way, an object that had shed billions of tons of itself with minimal visible structure compared to expectations. Think about that for a moment. 13%. If an object with an estimated mass of 33 billion tons loses 13%, we're talking about roughly 4 billion tons of material. That's the calculated scale based on analysis by Avi Loeb and other researchers tracking this object. And when something loses that much mass in space, especially near the Sun where heat turns ice into gas at explosive rates, there's supposed to be evidence. Spectacular, undeniable, visible from Earth evidence. A glowing tail of gas and dust that catches sunlight and announces to anyone watching that something profound is happening out there. That tail, the brilliant, unmistakable structure that should have stretched millions of kilometres, appeared far dimmer than expected. Before we go deeper into this mystery, I want to know something. Drop a comment telling me if you've been following this object since August when the first observations started rolling in, or if this is the first time you're hearing about mass loss of this magnitude from an interstellar visitor. If you are one of the early followers, you're part of a small community who recognised something genuinely unusual was happening here. And if this is your first time hearing about 3i Atlas's mysterious mass loss, welcome to one of the most intriguing astronomical puzzles unfolding in real time. Let me give you the context you need. 3i Atlas is the third confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017, that cigar-shaped mystery that sparked 1,000 debates and still divides scientists today. The second was Comet 2I/Borisov in 2019, which behaved pretty much exactly like we expected a comet to behave, almost boring in its predictability. Then came 3i Atlas, and from the beginning, nothing about this visitor has followed the script. We're not going to rehash the discovery story here. You already know it arrived from interstellar space. You already know it's following a hyperbolic trajectory that will carry it back out into the darkness between stars. What matters right now is what's happening to it as we speak, and what that behaviour is revealing, or rather, what it's hiding. Here's what scientists observed. Throughout August and into September of 2025, 3i Atlas was losing mass at what seemed like a normal rate for an active comet, about 330 pounds per second. That's substantial, sure, but not alarming. Comets do this. They're essentially dirty snowballs, and when they get close to the Sun, the ice sublimates directly into gas, carrying dust with it. Standard physics, expected behaviour. But then something changed. As 3i Atlas approached its perihelion, its closest point to the Sun, that mass loss rate didn't just increase, it exploded. By the time it reached perihelion on October 29th, 2025, at a distance of 1.36 astronomical units from the Sun, the object was hemorrhaging 4.4 million pounds of material every single second. Not per minute, not per hour, every second. Let that number settle in your mind. 4.4 million pounds every single second. That's the weight of multiple Boeing 747 aircraft being ejected into space with every tick of the clock. And this wasn't a momentary spike. This rate persisted through the perihelion passage. Scientists calculated that during this period of peak activity, 3i Atlas lost approximately 13% of its total mass, roughly 4 billion tons from an object estimated at 33 billion tons. Now when a comet loses mass at this rate, the material doesn't just disappear. It forms a coma, a glowing cloud of gas around the nucleus, and more importantly it creates a tail. Actually 2 tails. One made of ionized gas that gets pushed directly away from the Sun by solar wind, glowing blue and extending potentially millions of kilometers. Another made of heavier dust particles that follow a curved path, creating that classic sweeping arc we associate with great comets. Both components should be visible, both should be bright, both should be utterly unmistakable in telescope images. If you're thinking, okay, so 3i Atlas should have a massive brilliant tail, you're exactly right. That's what should have happened. Keep that expectation in mind as I show you what actually occurred. On November 5th, when 3i Atlas emerged from solar conjunction and became observable again, astronomers pointed their instruments toward the expected position. They were prepared to see a transformed object. They anticipated a brilliant display. What they captured instead was an image that triggered immediate confusion across research teams worldwide. An object that showed signs of activity, yes, but with a tail structure far too subdued for the amount of mass loss confirmed by other measurements. This is where the mystery becomes genuinely unsettling. The data confirming the mass loss is solid. It comes from multiple sources: spectroscopic analysis showing outgassing rates, brightness measurements indicating increased activity, and most tellingly, navigation data revealing changes in the object's trajectory consistent with massive material ejection. The evidence that 3i Atlas lost billions of tons is not in question. What's in question is where that material went and why we can't see it. Dr. Avi Loeb, the Harvard astrophysicist who chairs the Galileo project, ran the calculations that made headlines. 13% of the nucleus mass, he noted, should be trailing behind this object in a visible stream, not a faint wisp requiring specialized equipment. A substantial structure that any decent telescope should capture. His analysis wasn't speculative. It was straightforward physics based on the confirmed outgassing rates and the known properties of cometary material. Yet that expected tail isn't there. Not in images from professional observatories, not in data from space-based telescopes, not in follow-up observations conducted specifically to search for faint structures that might have been initially missed. The tail that physics demands should exist appears to be absent. So we're left with a paradox that has no easy resolution. Either our measurements of the mass loss are wrong, but they're confirmed by multiple independent methods, or our understanding of how cometary material behaves is incomplete. But we've observed hundreds of comets, and they all follow the same basic rules. Or something about 3i Atlas is genuinely different in ways that challenge our current models. Scientists don't like paradoxes. When observations don't match predictions, it means either the observations are flawed or the theory needs revision. In this case, the observations come from some of the most sophisticated instruments humanity has ever built. The James Webb Space Telescope, the Very Large Telescope in Chile, the ALMA Radio Observatory. These aren't amateur tools prone to error. They're precision instruments operated by teams who double-check everything. Which means we're facing the uncomfortable possibility that our theories about cometary behavior might be missing something crucial, that interstellar objects might operate under different rules than their solar system cousins, or that 3i Atlas isn't quite what it appears to be. Before we explore those possibilities, you need to understand exactly what happened during those critical weeks when this object passed through its closest approach to the Sun. Because the missing tail isn't the only anomaly, it's just the most visible one. There are others, subtle, strange, and deeply puzzling observations that together paint a picture of an object that refuses to behave the way physics textbooks say it should. So that's anomaly number 1. Keep that in your mind. Massive mass loss with barely any visible tail. Because when you see anomaly number 2, you'll understand why scientists are so puzzled. To understand why the missing tail is so troubling, you need to see what should have happened when 3i Atlas made its closest approach to the Sun. Because perihelion, that moment of maximum solar proximity, is when comets reveal their true nature. It's when heat becomes a transformative force, when dormant ice awakens into violent activity, and when objects that look like dark stones from a distance suddenly blaze with light and grow tails that dwarf planets in size. For 3i Atlas, perihelion arrived on October 29, 2025. The object swept to within 1.36 astronomical units of the Sun, roughly 204 million kilometers, just a bit farther than Earth's orbit. Now, by cometary standards, this isn't an exceptionally close approach. Some comets graze the Sun at distances measured in solar radii, plunging so deep into the corona that they either emerge transformed or don't emerge at all. But 1.36 AU is close enough, more than close enough to trigger the chain of events that defines cometary behavior. Here's what's supposed to happen, based on everything we know about comet physics. As the object approaches the Sun, solar radiation intensifies, surface temperatures climb, ice that has remained frozen for potentially billions of years begins to absorb energy. Eventually it reaches a critical threshold where solid ice transitions directly into gas, without passing through a liquid phase, a process called sublimation. This isn't gentle. When ice sublimates under solar heating, it explodes outward, creating jets of gas that carry dust particles with them. The nucleus becomes wrapped in a coma, a vast cloud of gas and dust that can extend hundreds of thousands of kilometers from the solid core. As outgassing continues, the material streaming away from the nucleus gets caught by two forces. Solar radiation pressure pushes the lighter gas particles directly away from the sun, creating the ion tail, a glowing stream that always points away from the solar direction, sometimes extending tens of millions of kilometers into space. Meanwhile, heavier dust particles follow a more curved path, influenced by the comet's orbital motion, creating the dust tail that sweeps behind the comet like a cosmic banner. This is textbook stuff. This is how comets have behaved since humans first started making detailed observations centuries ago. And this is exactly what scientists expected from 3I Atlas as it approached perihelion. Early signs suggested the script was being followed. Throughout September, observations from the Very Large Telescope in Chile began detecting increased activity. Spectroscopic analysis revealed the presence of specific molecules being released from the nucleus: hydrogen cyanide, carbon monoxide, and interestingly atomic nickel vapor, which gave scientists clues about the composition locked inside this interstellar visitor. The fact that these gases were appearing in increasing quantities meant sublimation was ramping up as expected. By late September, the outgassing rate of hydrogen cyanide alone had reached approximately 4.5 times 10 to the 25th power molecules per second. If you're not fluent in scientific notation, let me translate. That's 45 trillion molecules every second just of this one compound. The object was becoming demonstrably active. Then came the colour change. Earlier observations had shown 3I Atlas with a slightly reddish hue, consistent with organic compounds on its surface that had been processed by cosmic radiation over eons. But as perihelion approached, that colour shifted toward blue, the telltale signature of gas emission dominating over reflected sunlight. The coma was forming, the transformation was beginning, the brightness increased dramatically as well. In August, 3I Atlas required substantial telescope power to detect clearly. By mid-October, it had brightened considerably, exactly as you'd expect from an object experiencing intense solar heating and releasing vast quantities of reflective material. Everything was proceeding according to the standard cometry playbook. October 29th arrived. Perihelion. Maximum solar irradiance. This is when comets typically reach their peak activity, when outgassing rates hit their highest levels, when tails grow to their most spectacular dimensions. And 3I Atlas did indeed reach peak activity, that 4.4 million pounds per second mass loss rate we discussed earlier. The numbers confirmed an object in the throes of violent transformation. But here's where the script diverged from expectation in ways both subtle and profound. The mass loss rate itself, while extremely high, could technically fit within the range of possible cometary behaviour. We've observed comets that undergo explosive outbursts, sudden releases of material that briefly send mass loss rates soaring. The famous comet 17P/Holmes, for example, brightened by a factor of nearly 1 million in just 42 hours back in 2007, creating a coma that briefly became larger than the Sun. Comets can be dramatic. They can be unpredictable. What they can't do, or at least what they've never been observed doing, is lose billions of tons of material at these rates without producing a correspondingly massive tail structure. Because the physics is straightforward. Material leaving the nucleus at thousands of kilometers per hour doesn't just vanish, it follows predictable paths. Solar wind and radiation pressure act on it. Orbital mechanics govern its distribution. And the result is always a visible tail. Scientists preparing for the November observations anticipated seeing 3I Atlas transformed. They expected a robust ion tail glowing blue-green from ionized carbon monoxide and other gases. They expected a dust tail potentially millions of kilometers long, curving gracefully behind the nucleus. They prepared instruments to measure the tail's composition, its structure, its evolution over time. What they needed was for 3I Atlas to emerge from solar conjunction. You see, as the object passed perihelion, it was positioned nearly between Earth and the Sun from our perspective, a geometry that makes observation essentially impossible. The Sun's glare drowns out everything nearby, so there was a waiting period, a span of days when the object was transforming but remained hidden behind the veil of solar brilliance. Astronomers marked November 5th on their calendars as the date when 3 Atlas would emerge into observable sky, far enough from the Sun's position that telescopes could be safely pointed toward it. Take a look at this timeline visualization showing the observation gap. You can see how 3I Atlas disappeared behind the Sun's glare right when perihelion occurred, then emerged on November 5th into observable sky. Instruments that had been tracking this object since August, that had documented its journey inward and watched its activity increase, now turned toward the post-perihelion position with considerable anticipation. The images came back showing an object that had clearly been active. The coma was present, that diffuse cloud of material immediately surrounding the nucleus. But the tail, that vast trailing structure that should have been the dominant feature, was remarkably subdued. Initial analysis suggested perhaps the viewing geometry was unfavourable, that we might be looking at the tail edge-on, which could make it less prominent. This was the optimistic interpretation. Follow-up observations over subsequent days and weeks, from different observatories and different angles, continued to show the same puzzling absence. The spectacular tail that physics demanded simply wasn't manifesting in a way consistent with the confirmed mass loss rates. And this is where the scientific community's confusion began to crystallize into genuine concern. Because the numbers don't lie, and the numbers are telling two different stories. Story 1, massive outgassing confirmed by spectroscopy and trajectory analysis, indicating billions of tons of material released. Story 2, minimal visible tail structure, suggesting far less material than the measurements indicate. These stories shouldn't both be true simultaneously. Yet here we are, looking at datasets that seem to contradict each other, while both being verified by independent sources. Something is fundamentally wrong with this picture. Either the mass loss measurements are being misinterpreted, but how when multiple methods confirm them? Or the tail is there but somehow invisible to our instruments. But why would it be invisible when we can detect faint structures around other comets with ease? Or the material that left the nucleus didn't form a tail in the conventional sense. But where did 4 billion tons of matter go if not into a tail structure? Notice what's happening here. We now have our first major contradiction. The spectroscopy and brightness changes prove massive outgassing occurred. But the imaging suggests far less material than those measurements indicate. If you're feeling like something doesn't add up, you're thinking exactly like the astronomers studying this object. And it's about to get even more complicated. Let me walk you through the core impossibility that's driving the scientific debate around 3I Atlas, because this isn't a subtle discrepancy or a minor measurement uncertainty. This is a fundamental contradiction between what we observe and what the laws of physics tell us must be happening. Dr. Avi Loeb put it starkly in his analysis. If 3I Atlas lost 13% of its nucleus mass, based on estimated total mass, we're looking at roughly 4 billion tons of material. That substance had to go somewhere. When cometary ice sublimates, it doesn't teleport away. It doesn't cease to exist. It becomes gas and carries dust particles with it, and that mixture of gas and dust follows predictable trajectories governed by the object's motion, solar radiation pressure, and the solar wind. The math is actually straightforward. 4 billion tons of material, released over the course of weeks around perihelion, travelling away from the nucleus at typical cometary outflow speeds of several hundred meters per second, should create a tail structure extending millions of kilometers. That tail should contain enough material to reflect and emit sufficient light to be easily visible in even modest telescopes. We're not talking about a faint wisp at the edge of detectability. We're talking about a substantial structure that amateur astronomers should be able to photograph from their backyards. To put this in perspective, let's look at other comets for comparison. Comet Neowise, which graced our skies in the summer of 2020, developed a magnificent tail visible to the naked eye from dark locations. Estimates suggested Neowise's tail stretched roughly 16 million kilometers at its most impressive. The mass loss rate that created that spectacular display was substantial, but not dramatically different in scale from what 3I Atlas was experiencing. If anything, the confirmed outgassing rates from 3I Atlas during its perihelion passage exceeded what Neowise demonstrated. Yet Neowise gave us postcard-perfect images. Look at these comparison images side by side. On the left, Comet Neowise with its brilliant tail. On the right, 3I Atlas from November observations. The contrast is striking. Where there should be a comparable or even more impressive tail, there's barely detectable structure. A bright head, and a sweeping tail that photographers around the world captured in stunning detail. 3i Atlas, with its even more dramatic mass loss, should have produced something comparable or potentially even more impressive. Instead, images from November show an object with a modest coma and remarkably little tail structure. Now, you might be wondering, couldn't there just be something wrong with the observations? Maybe the tail is there, but we're just not seeing it? That's a fair question, and scientists ask the same thing. But before you think this might be an issue of telescope sensitivity or image processing, understand that multiple observatories using different instruments and different techniques have all reported similar findings. The Hubble Space Telescope, with its exquisite resolution and ability to detect faint structures, has observed 3i Atlas. Ground-based observatories with specialized narrowband filters designed to highlight specific gas emissions have pointed toward it. Radio telescopes capable of detecting molecular signatures have analyzed its output. The consensus from all these varied approaches is consistent. The expected tail is not manifesting. This has led to intense scrutiny of the observation data and the methods used to calculate mass loss. Could the spectroscopic measurements be overestimating the outgassing rates? Spectroscopy works by analyzing the light an object emits or reflects, looking for the characteristic signatures of specific molecules. When you detect hydrogen cyanide emission lines, you can calculate how much hydrogen cyanide is being released based on the intensity of those lines. It's a well-established technique used successfully on hundreds of comets. For 3i Atlas, multiple independent spectroscopic observations from different facilities arrived at similar conclusions about outgassing rates. The Very Large Telescope in Chile, the James Webb Space Telescope, the ALMA array, these aren't instruments prone to systematic errors that would all point in the same wrong direction. When multiple sophisticated facilities agree on a measurement, that measurement is likely accurate. So if the mass loss is real, where is the material? This is the question keeping planetary scientists up at night. There are several hypotheses being considered, and it's important to examine each one fairly. Hypothesis 1. Viewing geometry. Perhaps we're looking at the tail from an angle that makes it difficult to see. If Earth's position relative to 3i Atlas placed us nearly edge into the tail, it would appear compressed and much fainter than if we were viewing it from the side. This is geometrically possible. However, orbital mechanics tell us the relative positions of Earth and 3i Atlas during November, and while the geometry wasn't optimal, it wasn't so unfavourable that a tail of the expected magnitude should become essentially invisible. Moreover, observations continued through November and into December as the viewing geometry changed and the tail remained elusive. Here's the pattern emerging. Every potential explanation we examine fits some of the data but contradicts other parts. Hypothesis 2. Unusual composition. Maybe the material being released from 3i Atlas has properties that make it less visible than typical cometary material. For instance, if the dust-to-gas ratio is much lower than normal, if it's releasing mostly gas with very little dust, the tail would be fainter because dust is typically what makes comet tails so bright and visible. Gas tails glow through fluorescence and emission, but dust tails shine brightly by reflecting sunlight across a large area. This hypothesis has some support from the spectroscopic data. The gases being detected suggest the composition of 3i Atlas is unusual compared to solar system comets. It appears to be very rich in carbon dioxide and carbon monoxide, with less water ice than typical. This different composition might indeed affect how visible the outgassing products are. But here's the problem. Even pure gas tails should be visible when they contain the amount of material we're calculating was released. And if it's all gas with no dust, that raises another question. Where's the dust that should be mixed with the ice in any natural comet nucleus? Hypothesis 3. Fragmentation. Perhaps 3i Atlas didn't remain intact through perihelion. Maybe it broke apart, either into a few large pieces or into many smaller fragments. Fragmentation would increase the surface area dramatically, which would accelerate sublimation and could explain the extreme outgassing rates. If the object shattered into numerous small pieces, each surrounded by its own small coma, the collective mass loss could be high, while no single dominant tail forms, because the material is distributed across multiple nuclei. This is actually one of the more compelling explanations, and we'll explore it in depth shortly. For now, note that fragmentation has been looked for specifically in the observation data. Researchers have examined images carefully to see if multiple distinct nuclei are visible or if there's evidence of an expanding debris cloud. The results so far are ambiguous. There are hints of complexity in the inner coma structure, but no definitive confirmation of multiple separate pieces as of the most recent reports. Hypothesis 4. Rapid dissipation. Perhaps the material being released is somehow dispersing much more quickly than normal, becoming so diffuse so fast that it drops below visibility thresholds before forming a traditional tail structure. This would require some mechanism that spreads the material out more rapidly than the standard physics of solar radiation pressure and orbital motion would predict. It's difficult to imagine what that mechanism might be, but it remains a theoretical possibility. Each of these hypotheses has problems. Each requires either special circumstances or behavior that deviates from what we've observed in other comets. And this is what makes the 3I Atlas situation so scientifically valuable, even as it frustrates attempts at easy explanation. When an object doesn't fit our models, it's teaching us something. The question is, what? Avi Loeb, in his characteristically direct style, has raised the possibility that deserves mention even if it remains highly speculative. If an object is losing mass without creating a visible trail, one alternative explanation is that the mass loss isn't happening through conventional outgassing at all. What if the acceleration we're detecting, which we'll discuss in detail next, isn't caused by sublimation, but by some other mechanism? What if 3I Atlas isn't a comet in the traditional sense? Before anyone jumps to conclusions, let me be clear. The mainstream scientific interpretation remains that 3I Atlas is indeed a comet, likely with unusual composition or fragmentation that explains the anomalies. Loeb's more exotic hypotheses about technological origins are not accepted by the broader astronomical community and require extraordinary evidence that hasn't been presented. But the fact that a respected Harvard astrophysicist feels compelled to raise these questions at all tells you something about how puzzling this object's behavior truly is. What we can say with certainty is this: the conventional comet model, as currently understood, does not fully explain the observations of 3I Atlas. Either we're missing some aspect of the observations, some component of the tail that's there but we're not seeing correctly, or we're missing some aspect of the physics, some process that allows an object to lose mass in ways that don't produce traditional tail structures. Either way, 3I Atlas is pushing us to refine our understanding. And the missing tail isn't even the strangest part of this mystery, because there's another anomaly in the data that makes the whole picture even more perplexing. An anomaly that actually provides some of our best evidence that the mass loss is real, while simultaneously deepening the paradox. Now, if you're still with me, and I hope you are because this is where the mystery deepens even further, we need to look at another piece of evidence that both confirms the mass loss is real and makes the missing tail even more inexplicable. Now we get to the piece of evidence that confirms something unusual is definitely happening with 3I Atlas, even as it makes the missing tail even more inexplicable. This is the acceleration anomaly, and it's based on some of the most precise measurements NASA's Jet Propulsion Laboratory can make. When you track an object moving through the solar system, you're essentially watching it respond to gravity. The sun's immense mass pulls on everything, creating the orbital paths we observe. If you know an object's position, velocity, and the gravitational forces acting on it, you can predict with extraordinary precision where it will be in the future. This is celestial mechanics at its finest, mathematics that Newton began developing centuries ago, and that we've refined to such accuracy that we can navigate spacecraft across billions of kilometers and arrive exactly where and when we intended. But here's what makes comets tricky. They don't just respond to gravity. When a comet releases gas from its nucleus, that gas carries momentum. It shoots out in specific directions, and by Newton's third law, every action has an equal and opposite reaction, the nucleus experiences a push in the opposite direction. It's the rocket effect in miniature. The comet becomes a tiny spacecraft with thrusters firing asymmetrically as the sun's heat triggers outgassing from whatever surface areas are exposed. This is called non-gravitational acceleration, and it's a well-documented phenomenon. Dozens of comets show measurable non-gravitational forces affecting their trajectories. The effect is usually small but detectable with precise orbit determination techniques. By carefully tracking how a comet's position deviates from the purely gravitational prediction, scientists can infer that outgassing is occurring and even estimate its magnitude. For 3I Atlas, navigation engineer Davide Farnocchia at NASA's Jet Propulsion Laboratory has been meticulously tracking the object's trajectory. Farnokia specializes in orbit determination for near-Earth objects and comets. He's the person calculating where things are going with the precision required for spacecraft navigation and impact risk assessment. When he analyzes an object's motion, you can trust the numbers. His analysis of 3I Atlas revealed clear evidence of non-gravitational acceleration. The object isn't moving purely under the sun's gravitational influence. Something is pushing it, causing deviations from the predicted gravitational path. That something, according to standard comet physics, should be outgassing, jets of gas erupting from the surface and imparting momentum to the nucleus. The magnitude of this acceleration corresponds to exactly what you'd expect from an object experiencing the intense outgassing suggested by the spectroscopic observations. In other words, the navigation data confirms the conclusion from the spectroscopy. The object is losing mass rapidly enough to measurably alter its trajectory. This is actually reassuring in a sense. Two completely independent measurement techniques are arriving at the same conclusion about the object's activity level. But here's where the reassurance evaporates, and the paradox deepens. If the non-gravitational acceleration is caused by outgassing, and if the outgassing is intense enough to detectably change the orbit of a multi-billion-ton object, then the amount of material being expelled is enormous. And enormous amounts of expelled material form visible tails. That's not speculation. That's observed reality from every other comet that's ever shown non-gravitational acceleration. Let me make this crystal clear. The acceleration detected by JPL navigation tracking tells us that 3I Atlas is experiencing forces consistent with massive outgassing. The spectroscopy tells us that massive outgassing is occurring and quantifies the gases being released. But the imaging tells us that the tail which must form from this massive outgassing isn't substantially visible. These three data streams should all be telling the same story. Instead, they're telling parts of different stories that don't quite fit together. The Atacama Large Millimeter Array, that extraordinary radio telescope installation in the Chilean desert, provided additional precision to the mystery. ALMA observed 3I Atlas in November and detected molecular emissions consistent with ongoing activity. But more interesting was what ALMA's positional measurements revealed. The object's location in the sky was off from the predicted position by approximately 4 arc-seconds, a tiny angular measurement, but statistically significant when you're using ALMA's precision. 4 arc-seconds might not sound like much, and in everyday terms it isn't. It's roughly the angle subtended by a dime viewed from a distance of about a kilometre. But in astrometry, the science of measuring celestial positions, 4 arc-seconds is meaningful. It indicates that the object has indeed received a kick from some force beyond simple gravity, and the direction and magnitude of that kick align with what you'd expect from significant outgassing. As of the most recent tracking data, 3I Atlas is moving at approximately 244,600 km per hour. That's its speed relative to the Sun, and a substantial component of that velocity represents the boost it received during its perihelion passage. Part of that boost came from gravitational acceleration as it fell toward the Sun and then swung back out. That's the slingshot effect that changes any object's speed when it whips around a massive body. But part of that boost, the navigation data suggests, came from the rocket effect of outgassing. This is where you start to appreciate the full depth of the mystery. We have multiple independent lines of evidence all confirming that 3I Atlas experienced intense outgassing around perihelion. We have the spectroscopic detections of gas molecules. We have the navigation data showing non-gravitational forces. We have the brightness changes indicating increased activity. We even have the observed colour shift to blue, consistent with gas emission becoming dominant. Everything points to a comet that was, during October and early November, vigorously active. Everything, that is, except the images that should show the tail. Notice what we have now. This is anomaly number 2 layered on top of anomaly number 1. The acceleration proves massive outgassing occurred. But the missing, or barely visible tail suggests that massive outgassing didn't leave the expected visible trail. These two facts shouldn't coexist. If you're feeling cognitive dissonance right now, that's exactly what scientists are experiencing. So here's the paradox stated as plainly as possible. The evidence for mass loss exists and is robust. The acceleration proves material was expelled with enough force to alter the orbit. The spectroscopy proves specific molecules were released in vast quantities. But the trail of material, the visible consequence that must follow from these conditions, is not substantially present in the observations. Either there's a tail and we're somehow not seeing it properly despite multiple sophisticated instruments looking for it, or there's no conventional tail, and we need to explain how billions of tons of matter can leave an object without forming one. Some scientists have suggested that perhaps the outgassing occurred in brief, intense bursts, rather than as a steady emission. If material was released in sudden explosions from specific active regions, the tail might be more dispersed or less structured than typical. There's precedent for this. Some comets are known to undergo outbursts where they suddenly release large amounts of material in short time frames. But even outburst material forms clouds and tails. It doesn't vanish. Others have wondered whether the material is there but is composed of particles with unusual properties that make them less efficient at scattering sunlight. Perhaps the dust grains are unusually small, or unusually dark, or have some other characteristic that reduces their visibility. This would be an unprecedented composition difference from known comets, but 3I Atlas is interstellar in origin. Maybe objects from other star systems simply have different properties than we're accustomed to. What nobody is seriously suggesting is that the acceleration is imaginary, or that the spectroscopy is completely wrong. The measurements are too solid, from too many independent sources. Something real happened to 3I Atlas during its solar passage. Something that involved significant mass loss and created forces strong enough to alter its trajectory measurably. The question remains, where did all that material go, and why can't we see it where we expect to? Before we can answer that, we need to consider the possibility that the object itself might not be intact anymore, that what we're observing might not be a single nucleus, but the remnants of something that broke apart under solar stress. Before we explore whether fragmentation might explain this paradox, let me remind you why this matters so much right now. We have a limited window to observe this object. December 19th is approaching. That's when 3I Atlas makes its closest approach to Earth, and we'll have our best chance for detailed observations. Every day it travels farther, becoming harder to study. The answers we're seeking, we may only have weeks to find them. Here's where this mystery could either be solved or become even stranger. There's a scenario that's both violent and elegant in its simplicity. A scenario that could potentially explain almost everything we've observed. But there's a problem with this explanation. A big one. What if the object didn't survive its perihelion passage intact? What if, instead of a single nucleus experiencing unusual outgassing, we're looking at the debris field of a comet that broke apart under the intense thermal and tidal stress of solar proximity? Comets are fragile. This isn't speculation, it's demonstrated fact. We've watched comets fragment and disintegrate in real time. Some break apart gradually over multiple orbits, shedding pieces each time they approach the Sun until nothing substantial remains. Others undergo catastrophic fragmentation in a single dramatic event, transforming from a solid nucleus into a swarm of smaller pieces in a matter of hours or days. The most spectacular example most people know is Comet Shoemaker-Levy 9, which broke apart during a close approach to Jupiter in 1992. When it returned to Jupiter 2 years later, it wasn't a single object but a string of fragments that impacted the giant planet in sequence, leaving dark scars in Jupiter's atmosphere visible even in small telescopes. That comet didn't fragment because of solar heat. It was torn apart by Jupiter's immense gravitational tidal forces. But the lesson is clear. Comets can, and do, break apart. For fragmentation closer to the Sun, consider Comet 332P/Ikea Murakami, which was observed splitting into multiple pieces in 2016. Hubble Space. Telescope images captured the breakup beautifully, showing 25 or more separate fragments drifting apart, each surrounded by its own small coma. Or Comet 73P/Schwarzmann-Wachmann 3, which fragmented into dozens of pieces and has been observed splitting further during subsequent perihelion passages. So fragmentation happens. The question is whether it happened to 3I Atlas. Avi Loeb has suggested that fragmentation might explain the unusual observations. His hypothesis goes like this. If the object broke into numerous substantial fragments, 16 or more in some scenarios he's outlined during or shortly after perihelion, the total surface area exposed to solar radiation would increase dramatically. More surface area means more ice directly exposed to sunlight. More exposed ice means much higher sublimation rates. You could potentially explain the extreme outgassing detected spectroscopically as the result not of unusually vigorous activity from a single nucleus, but of normal activity from many pieces simultaneously. The math is actually quite compelling. Imagine a spherical object. Let's keep the geometry simple, with radius r. Its surface area is proportional to r squared, while its volume is proportional to r cubed. Now imagine that object breaks into 16 equal pieces. Each piece has a radius of roughly r divided by 2.5. The surface area of each fragment is much less than the original sphere, but now you have 16 of them. When you add up all their surface areas, the total exposed surface is significantly larger than the original single object had. More surface area means more sublimation for the same solar input. If 3I Atlas fragmented into many pieces, each undergoing normal cometary outgassing, the collective mass loss could easily reach the rates that spectroscopy and navigation data indicate, without requiring any single piece to behave unusually. This would also potentially address the tail mystery. If you have 16 separate nuclei, each producing its own small coma and tail, but those tails are not aligned because the fragments have slightly different trajectories and are tumbling in different orientations, the result might be a diffuse cloud of material rather than a single organized tail structure. From a distance, this could appear as a substantial coma without the clear linear tail feature we normally associate with comets. So fragmentation is an attractive hypothesis. It explains the high activity. It potentially explains the unusual tail appearance. And it would mean that nothing about fundamental physics is wrong. It's just that we're looking at a different configuration than we initially assumed. The obvious question becomes, is there evidence that 3I Atlas fragmented? Astronomers have been looking carefully. When a comet breaks apart, there are telltale signs. The most obvious is that you should see multiple distinct condensations in the coma, bright spots indicating separate nuclei, each the center of its own activity. If the fragments are large and separated enough, even ground-based telescopes can resolve them as distinct objects. Hubble and other high-resolution instruments have been pointed at 3I Atlas specifically to search for this signature. The inner coma, the region immediately around the nucleus, has been examined with care. This doesn't mean fragmentation definitely didn't occur. It means we can't yet confirm it with certainty. We're in a we don't know yet situation, not a definitely didn't happen situation. There are suggestions of structure and asymmetry in the inner coma, hints that perhaps multiple sources of activity exist, but no absolutely clear detection of well-separated fragments. This doesn't mean fragmentation didn't occur. It might mean the fragments are too close together to resolve clearly, or that they're too small individually to stand out against the collective brightness of the coma. Or it might mean that if fragmentation happened, it resulted in the nucleus breaking into a rubble pile, a collection of pieces that remain gravitationally bound to each other, essentially a loose aggregate rather than completely separate objects. The ExoMars Trace Gas Orbiter, a spacecraft currently in orbit around Mars, has turned its cameras toward 3I Atlas during favourable geometry when the comet passed within view. Mars orbiters occasionally contribute to solar system observations when their instruments can be spared from Mars science. The images from ExoMars TGO provided another viewing angle, and while they confirmed activity around 3I Atlas, they also didn't show definitive evidence of widely separated fragments. Ground-based observatories have continued monitoring as well. Automated systems scan images looking for changes, any indication that the central condensation is splitting or that multiple nuclei are separating. So far, no smoking gun. But absence of evidence is not evidence of absence, especially when the observations are challenging due to the object's distance and brightness. There's another aspect to consider. If 3I Atlas fragmented, when did it happen? Was it a sudden catastrophic breakup right at perihelion, or a more gradual separation over days or weeks? The timing matters because it affects what we should observe. Imagine a scenario where the object held together until perihelion, then broke apart suddenly under thermal stress as the most intense solar heating occurred. The initial observations in September and early October would show a single nucleus behaving normally. Then, during the conjunction period when we couldn't observe it, fragmentation occurred. When it emerged in November, it was already multiple pieces, which is what we've been observing since. This timeline would fit the data reasonably well. The problem is we have a gap in the observations precisely when the most critical changes were happening. It's frustrating from a scientific standpoint, but it's unavoidable. You simply cannot observe an object when it's nearly in line with the Sun from Earth's perspective. The glare makes it impossible, and pointing a telescope that close to the Sun risks damaging the instrument. Alternatively, perhaps fragmentation began earlier but was subtle, with small pieces separating gradually. This might explain why outgassing rates were increasing even before perihelion, not because of increasing solar heat alone, but because increasing surface area was being exposed as the object developed cracks and shed fragments. Or perhaps fragmentation didn't happen at all, and we're overcomplicating what is simply a comet with unusual composition and an unlucky viewing geometry that makes its tail appear less prominent than it actually is. The honest answer is that we don't yet know with certainty whether 3i Atlas is intact or fragmented. The observations are consistent with either scenario, though each scenario requires certain assumptions about what we're not seeing clearly. More observations over the coming weeks and months will hopefully clarify the situation. If the object is fragmented, the pieces should gradually separate further, becoming easier to distinguish individually. If it's intact, continued monitoring should eventually reveal more about the structure and extent of any tail material that's present. What we can say is that fragmentation remains one of the more scientifically reasonable explanations for the combined observations. It doesn't require exotic physics. It doesn't demand that we rewrite textbooks. It just requires that a fragile object subjected to intense solar heating did what many comets have done before, broke apart. But whether fragmented or whole, there's another piece to this puzzle that makes 3i Atlas particularly intriguing: its chemical composition, which has revealed itself to be distinctly unusual compared to the comets we're familiar with in our own solar system. Let me take you through the timeline of what we've observed with 3i Atlas, because when you lay out the sequence of events, you start to see a pattern of escalation that raises questions about what was happening inside this object as it plunged toward its encounter with the Sun. This isn't just a story about one strange observation, it's a chronicle of transformation unfolding across months, each phase revealing new details that deepened the mystery. August 2025. This is our baseline. By this point, 3i Atlas had been identified as an interstellar visitor, and observatories were beginning systematic monitoring. The James Webb Space Telescope, that marvel of engineering orbiting the Sun-Earth L2 point, turned its infrared instruments toward the object. What Webb saw was an object showing modest but clear cometary activity. The outgassing rate was measured at approximately 330 pounds per second. Substantial, definitely indicative of an active comet, but not extraordinary. Webb's spectroscopy revealed the presence of carbon dioxide and carbon monoxide being released from the nucleus. The object appeared slightly reddish in colour, consistent with organic compounds on its surface that had been modified by billions of years of cosmic ray exposure during its journey through interstellar space. September brought increasing activity. The Very Large Telescope in Chile, perched on Cerro Paranal in the Atacama Desert with some of the clearest skies on Earth, began detailed spectroscopic observations. On September 14th specifically, VLT detected hydrogen cyanide emissions at a rate of approximately 4.5 times 10 to the 25th power molecules per second. For context, hydrogen cyanide is common in comets. It's one of the standard molecules we look for as a tracer of cometary composition. But the rate at which it was being released was significant and climbing. More intriguingly, VLT also detected atomic nickel vapor. Nickel in comets had only been discovered a few years prior, and its presence tells us something about the mixture of rock and ice that comprises the nucleus. The detection of nickel vapor meant that 3i Atlas wasn't just releasing ices, it was releasing refractory materials, suggesting either that the ices were mixed intimately with rocky components, or that the heating was beginning to affect more than just the surface volatiles. September also saw the colour beginning to shift. That reddish hue started giving way to bluer tones, as gas emission became increasingly dominant over reflected sunlight. This is the expected transition for a comet becoming more active. The coma grows, filled with gas that emits light at specific wavelengths, particularly in the blue and green parts of the spectrum, where ionized carbon monoxide and other molecules fluoresce under solar ultraviolet radiation. Early October, and the brightening became more obvious. The object was still months from perihelion, but was already demonstrating that it would be an active performer. Astronomers revised their predictions upward regarding what the perihelion passage might reveal. Excitement built in the community. An active interstellar comet approaching the Sun is a rare opportunity to study material from another star system as it responds to solar heating. October 29th. Perihelion. 1.36 astronomical units from the Sun, roughly 204 million kilometers. This was the moment of maximum stress. Solar radiation at this distance is intense, not as fierce as Mercury experiences, but more than sufficient to drive vigorous sublimation from any ices present on or near the surface. This was when the outgassing rate exploded to that staggering 4.4 million pounds per second. This was when the 13% mass loss that defines our entire mystery occurred over a span of days to weeks around this closest approach. And this was when we lost the ability to observe the object. For approximately a week, 3i Atlas was too close to the Sun's position in Earth's sky to be safely observed. Telescopes were blind to whatever transformation was occurring. Was it breaking apart? Was it developing the massive tail that the mass loss rate predicted? Was something unexpected happening that, if we'd seen it in real time, would have clarified the entire mystery? We simply don't know. There's a gap in the observational record precisely when the most interesting events were unfolding. November 5th. The date circled on every observer's calendar. This was when 3i Atlas emerged from solar conjunction, when it had separated enough from the Sun in angular terms that observations could safely resume. Telescopes across the globe and in space had been preparing for this moment. The anticipation was real. This would be our first look at the post-perihelion object, the reveal of what all that intense heating had wrought. The images came back, and the confusion began. Activity, yes. A coma, certainly. But the tail, that spectacular structure that should accompany an object that had just lost billions of tons, was strangely subdued, far fainter than the confirmed mass loss would predict. The navigation data confirmed the non-gravitational acceleration, proving that massive outgassing had indeed occurred. But the visual signature of that outgassing was strangely muted. This was the beginning of the head-scratching that continues to this day. Through mid and late November, observations continued. Different instruments, different techniques, all trying to understand what they were seeing. The ALMA array in Chile provided its radio observations, detecting continued molecular emissions and contributing to the precise position measurements that revealed the acceleration. The ExoMars orbiter provided its perspective from Martian space. Ground-based observers with large telescopes added their data points, and as November turned into December, the picture remained puzzling, but relatively stable. 3i Atlas continued to show activity consistent with ongoing outgassing, though reduced from the perihelion peak as you'd expect for an object moving away from the Sun. The tail situation remained ambiguous. Structure was present, but not the spectacular feature that the mass loss calculations predicted. December 19th, 2025. Mark this date. This is when 3i Atlas reaches its closest approach to Earth, approximately 1.8 astronomical units, or about 269 million kilometers. That's still a considerable distance, farther than the Sun is from us, but it's the best viewing geometry we're going to get. This is when Earth-based telescopes will have their optimal chance to resolve fine details, to search definitively for fragmentation signatures, to measure tail structures with maximum sensitivity. As of now, that date is still ahead of us. Observatories are preparing, programs are scheduled. The astronomical community is hoping that this close approach will provide the clarity that earlier observations couldn't deliver. Will we finally see clear evidence of multiple nuclei if the object is fragmented? Will we detect tail structures that were previously too faint or poorly positioned to observe clearly? Or will 3i Atlas continue to guard its secrets? Looking further ahead, March 2026 brings another milestone. 3i Atlas will pass relatively close to Jupiter's orbit on its way out of the inner solar system. While it won't have a close encounter with Jupiter itself, this marks the beginning of the end for easy observations. Beyond Jupiter's distance, the object will grow increasingly faint as it recedes from the Sun, and the opportunities to study it will diminish rapidly. By mid to late 2026, 3i Atlas will likely have faded beyond the reach of all but the largest telescopes, and eventually it will slip away entirely, heading back into the darkness between stars from which it came. We will have lost our chance to answer the questions it poses. This creates genuine urgency in the observation campaigns. The window to understand this object is measured in months, not years. And as that countdown proceeds, there's another layer to the mystery we need to examine: the composition of the material that makes up this interstellar visitor, because the chemical analysis has revealed that 3i Atlas is made of stuff that doesn't quite match what we're used to seeing in comets from our own solar system. The composition of 3i Atlas revealed something that nobody expected. What is this object made of? The question sounds simple, but when JWST and the VLT analysed the chemical signatures, they found something that doesn't quite match normal comets, and this unusual chemistry might be a key piece of the missing tail puzzle, an object whose chemistry is teaching us that not all comets are created equal, and that objects from other star systems may carry compositions shaped by environments and processes fundamentally different from what created our own solar system's reservoir of icy bodies. The James Webb Space Telescope, with its extraordinary infrared capabilities, has provided the most detailed compositional analysis. Webb's spectrometers break down the light from 3I Atlas into its component wavelengths, and within that spectrum are the fingerprints of specific molecules. Each chemical compound absorbs and emits light at characteristic frequencies, creating a unique signature that allows us to identify it even across interstellar distances. What Webb found is a comet dominated by carbon compounds in unusual proportions. Carbon dioxide appears to be the primary volatile, the main ice component that's sublimating as the object is heated. This is noteworthy because in typical solar system comets, water ice is usually the dominant volatile. Comets from our Oort cloud or Kuiper belt are fundamentally dirty snowballs where water ice makes up the majority of the frozen material, with other compounds like carbon dioxide, carbon monoxide, and methane present in smaller amounts. 3I Atlas appears to have the proportions flipped. It's rich in carbon dioxide and carbon monoxide with water present, but seemingly in much smaller relative amounts than we'd expect. This isn't unprecedented. We've observed some solar system comets with unusual compositions, but it's distinctive enough to stand out. Why would an interstellar comet have such a different composition? One possibility relates to where and how it formed. Our solar system's comets are thought to have originated in different regions. Kuiper belt objects formed in the outer solar system beyond Neptune, in a region where water ice was stable but the temperature was still relatively warm by cosmic standards. Oort cloud comets are believed to have formed closer to the giant planets and then been gravitationally scattered outward, but they still condensed from the same nebular material that formed our Sun and planets, a mixture with specific elemental ratios determined by the composition of the molecular cloud that collapsed to form our solar system. 3I Atlas formed in a different star system, from a different primordial molecular cloud. That cloud may have had a different ratio of carbon to oxygen than our solar nebula had. It may have formed in a region of its home system where temperatures were different, causing different compounds to condense into ices. The star it formed around may have been a different type than our Sun, influencing the chemistry through different radiation environments. All these factors could lead to comets that are compositionally distinct from ours. There's another possibility that's been raised, and it's fascinating in its implications. Suppose 3I Atlas formed with a composition not radically different from solar system comets. It then spent potentially billions of years travelling through interstellar space, exposed to galactic cosmic rays, high-energy particles that pervade the galaxy, including protons and heavier nuclei accelerated to near-light speed by supernova remnants and other energetic processes. Galactic cosmic rays, when they strike ice, cause radiolysis. They break molecular bonds and rearrange atoms, driving chemical reactions that wouldn't normally occur at the frigid temperatures of interstellar space. Over millions or billions of years, this cosmic ray processing can significantly alter the composition of surface and near-surface materials. Water ice can be broken down, with hydrogen escaping to space and oxygen recombining into other compounds. Carbon-bearing molecules can be synthesized. The result is a radiation-processed mantle that might have a very different composition than the pristine interior. If this is what happened to 3I Atlas, then what we're observing when we analyze its outgassing isn't necessarily the bulk composition of the object. We might be seeing primarily the altered surface material processed by eons of cosmic ray exposure. The interior might still be rich in water ice, but that deeper material isn't being exposed and sublimated, at least not yet. Only if the object fragments, or if intense heating erodes through the processed mantle, would we begin to see what lies beneath. This scenario is speculative but not implausible. It would actually help explain some of the unusual behaviour. A radiation-processed surface mantle might sublimate differently than pristine ice. It might have different mechanical properties, affecting how and when the nucleus sheds material. It might contain components that are more or less volatile than standard comet ices, leading to unexpected activity patterns. The detection of nickel vapour adds another puzzle piece. Nickel is a refractory element. It's typically locked up in rock and mineral grains, not in ices. For it to appear as vapour in the coma, it needs to be either heated to very high temperatures or somehow incorporated into the sublimating ices in an intimate mixture. The presence of nickel suggests that the boundary between rock and ice in 3I Atlas might not be as clear as in typical comets. By now, you've probably noticed a theme running through this investigation. Every characteristic of 3I Atlas is unusual but not impossible. Subdued tail? Strange, but maybe explainable. Acceleration without visible outgassing trail? Paradoxical, but perhaps composition helps account for it. Each piece individually could have an explanation, but all together? That's where it crosses from unusual into genuinely mysterious. Perhaps the object is a more homogeneous mixture of rocky and icy components, rather than a clearly differentiated structure. This relates to the broader question of how comets form. The traditional model envisions ices condensing in the cold outer regions of a protoplanetary disk, with dust and small rocky particles mixed in but largely separate. But if 3I Atlas formed through a different process, perhaps in a more turbulent environment, or through collisions that intimately mix materials, or in a disk with different properties, the resulting structure could be quite different from what we're familiar with. When you compare 3I Atlas to the previous interstellar visitor comet, 2I/Borisov, the contrast is instructive. Borisov, discovered in August 2019, was studied intensively during its transit through our solar system. Its composition, as measured by spectroscopy, looked remarkably similar to solar system comets. It had substantial water, along with carbon monoxide and other typical cometary volatiles in familiar ratios. Its behaviour during perihelion passage was textbook. It developed a nice tail, it outgassed predictably. It basically acted like a comet from our own Oort cloud that happened to be passing through on a hyperbolic trajectory. Borisov suggested that comet formation might be a universal process, producing similar objects regardless of which star system they form around. It implied that the physics and chemistry of planet formation are consistent enough across different stellar environments that the end products are comparable. 3I Atlas suggests something different. It suggests that there's more diversity in the population of comets across the galaxy than one example would indicate. It tells us that we can't assume every interstellar comet will behave like the ones we know, and that's actually scientifically exciting, even as it makes interpretation more difficult. The composition also factors into the interpretation of the missing tail. If the outgassing is dominated by carbon dioxide rather than water, and if the dust-Togas ratio is lower than typical, meaning less solid dust mixed with the sublimating ices, then the material being released would be more gaseous and less dusty. Dust is what makes comet tails bright and easily visible, because dust particles efficiently scatter sunlight. A mostly gaseous tail would be fainter, relying on emission from ionized molecules rather than reflected light. But again, even taking this into account, the calculated amount of material that was released should still produce a more visible structure than what's being observed. The composition is unusual, yes, but it's not so exotic that it completely explains the anomaly. It might be part of the explanation, one factor among several, but it's not the whole answer. As spectroscopic observations continue, scientists are watching for any changes in the composition of the outgassing. Are the ratios of different molecules staying constant, or are they shifting as the object moves away from the Sun? If the surface is depleted of more volatile compounds and now less volatile materials are beginning to sublimate, we might see the composition change over time. That would tell us something about the layering and structure of the nucleus. Similarly, if fragmentation has occurred and different fragments have slightly different compositions, perhaps because they broke along boundaries between different material zones, then comparing the spectra from different pieces could reveal information about internal structure that we'd never otherwise be able to access. The chemical story of 3I Atlas is still being written. Each observation adds data points, and gradually a picture is emerging of an object that's definitely a comet in the fundamental sense, a mixture of ice and rock that outgasses when heated, but one that carries a chemical signature shaped by a history we're only beginning to understand. Which brings us to the question that's been building throughout this entire discussion. What do we actually know? What remains unknown? And what should we be watching for as this interstellar visitor continues its journey through our neighbourhood? Here we are, tens of thousands of words into the mystery, and the honest truth is that we still don't have definitive answers. What we have is data. Lots of it, from multiple instruments analysed by skilled scientists using established techniques. What we have is a collection of observations that don't quite fit together into a coherent picture. What we have is an object that refuses to behave entirely as expected, and in that refusal lies either a profound lesson about interstellar comets or a puzzle that will frustrate researchers for years to come. Let's be clear about what the central questions are, because it's easy to get lost in the details and lose sight of the core mysteries. Question 1. Where did the mass go? 13% of the nucleus mass, approximately 4 billion tons based on estimated total mass calculations, was released during the weeks around perihelion. Question 2. Is 3I Atlas intact or fragmented? Question 3. What does the unusual composition tell us? Question 4. What is the nature of the non-gravitational acceleration? These are not trivial questions. They're the kind of puzzles that doctoral dissertations get written about, that journal articles debate, that conference presentations dissect. And they all stem from one object, one interstellar visitor that had the audacity not to behave like the textbook suggested it should. Now let's talk about the range of scientific perspectives, because this is where we need to be careful and honest about what's mainstream interpretation and what's speculative edge science. The conservative mainstream view held by most planetary scientists is that 3I Atlas is indeed a comet, an icy body from another star system experiencing solar heating and outgassing. The anomalies we're seeing in this view are explained by some combination of fragmentation, unusual composition, unfavourable viewing geometry, and perhaps aspects of the observation timing that we haven't fully appreciated. Nothing about 3I Atlas requires new physics or exotic explanations. It's just a comet that's teaching us that interstellar comets have more diversity than we realised from the single previous example of Borisov. This is a reasonable, measured interpretation. It doesn't overclaim. It acknowledges the puzzles but expresses confidence that continued observations and analysis will eventually resolve them within the standard framework of cometary science. Most researchers working on 3I Atlas probably hold something close to this view, even as they actively investigate the anomalies. Then there's a more speculative position, most prominently represented by Avi Loeb. Loeb has suggested that if an object shows characteristics that don't fit cometary behaviour, such as acceleration without visible outgassing trails, then we should consider alternative explanations, including the possibility of a technological origin. He's not claiming this is definitely the case with 3I Atlas, but he's raising it as a hypothesis that deserves consideration if natural explanations continue to fall short. To be absolutely clear, the broader astronomical community does not accept technological explanations for 3I Atlas. There is no compelling evidence that the object is anything other than natural. Loeb's perspective is viewed as fringe by most of his colleagues, and his history of suggesting possible technological origins for astronomical phenomena, most notably with Oumuamua, has made many scientists dismissive of his interpretations. But here's why I mention it. Not because I'm endorsing exotic explanations, but because the fact that a Harvard astrophysicist with a substantial publication record feels compelled to raise these possibilities tells you something about how genuinely puzzling 3I Atlas is. When standard models don't immediately and obviously explain observations, when there are gaps and contradictions in the data, that's when alternative hypotheses start to be voiced. Most of those alternatives will turn out to be wrong, but occasionally anomalies do point to something genuinely new. But I also want to be clear about what I want you to take away from this investigation. It's not certainty, it's intellectual humility and excitement. Humility because an object less than a kilometre across can still baffle our best instruments and brightest minds. Excitement because every puzzle is an opportunity to learn something new about how the universe works. With perhaps unusual characteristics, but a comet nonetheless. The most likely explanation for the observations probably involves fragmentation that we haven't been able to confirm clearly yet, combined with composition effects that alter how visible the outgassing products are. I suspect that as observations continue, especially around the December 19th Earth closest approach, we'll get clarity that resolves most of the mystery. But I also recognise that I could be wrong. Science has a history of anomalies that initially seemed like minor puzzles, but turned out to be signals of something profound. The precession of Mercury's orbit that didn't quite fit Newtonian gravity turned out to require Einstein's general relativity to explain. The dimming patterns of Tabby's star that sparked alien megastructure speculation turned out to be dust, but they drove intense observation that taught us new things about stellar variability. Anomalies are how science progresses. So what happens next? What should we be watching for? December 19th is the immediate milestone. That's when 3i Atlas makes its closest approach to Earth at approximately 269 million kilometers. The viewing geometry will be optimal. Telescopes will be trained on it with the best spatial resolution we're going to get. If there are fragments separated by even modest distances, we should be able to resolve them. If there are faint tail structures that earlier observations missed, we'll have our best chance to detect them. Through January and February of 2026, observations will continue as the object recedes. We'll be watching for any evolution in the activity level, any changes in composition as different layers of the nucleus are exposed, any late-stage fragmentation events. The farther it gets from the Sun, the less active it will become, but that reduction in activity follows predictable patterns, and deviations from those patterns would be informative. By March, 3i Atlas will be passing near Jupiter's orbital distance on its outbound trajectory. There's been some discussion of whether the JUICE spacecraft, the European Space Agency's Jupiter Icy Moons Explorer, currently en route to the Jovian system, might have any opportunity to observe 3i Atlas if the geometry works out. That's uncertain, but even a distant observation from a different vantage point could provide valuable data. Beyond mid-2026, observations will become increasingly difficult as the object fades and grows more distant. Eventually, only the largest telescopes will be able to detect it, and finally it will slip beyond even their reach, becoming once again just another dark ice ball drifting through the void between stars. We will have had perhaps a year of good observations, maybe a bit more if we're fortunate. A single year to study a visitor from another star system, and then it's gone, carrying whatever secrets we failed to unravel back into the darkness. This is the nature of astronomy. Opportunities appear on timescales we don't control. Objects arrive unannounced, on trajectories that give us limited observation windows, and then depart whether we finish studying them or not. We work with what we get. We extract every bit of information we can, and we accept that some questions may remain unanswered. What's your theory? Tell me in the comments. Are you in the "it's an unusual comet with unlucky viewing geometry" camp? Do you lean toward fragmentation as the key explanation? Or do you think there's something about interstellar objects we fundamentally don't understand yet? The community discussing this mystery is growing, and some of the most insightful observations have come from viewers who notice details that get overlooked. Share your theory, and let's solve this together. That makes its tail less visible than we expect. Do you lean toward fragmentation as the explanation for the extreme activity without the corresponding visible tail? Or do you wonder whether there's something about interstellar objects we fundamentally don't understand yet? Drop your thoughts in the comments. I'm genuinely curious what perspective you're bringing to this mystery. And here's what I'll say as we close this examination of one of the most puzzling objects currently in our sky. 3i Atlas, whatever it ultimately turns out to be, is a reminder that the universe still holds surprises. In an age where we can model galaxy collisions and detect gravitational waves from black holes billions of light years away, a single icy object less than a kilometer across can still baffle us. That's humbling. It's also exhilarating. Because every puzzle is an opportunity. Every anomaly is a doorway to deeper understanding. The objects that don't fit our models are often the ones that teach us the most, forcing us to refine our theories, to question our assumptions, to look more carefully at what we think we know. Is 3i Atlas teaching us that interstellar comets follow different rules than solar system comets, shaped by different formation environments and modified by eons of cosmic ray exposure? Or is something even stranger happening, behavior that will require us to expand our framework for what's possible? We may have our answers in weeks, as the December observations provide new data. Or this may remain an unsolved puzzle, a footnote in astronomical history, the interstellar comet that got away before we fully understood it. Either way, I'll be watching. I'll be following the observation reports as they're published, reading the analysis papers as they appear, and bringing you updates as this story develops. Because this is what science looks like in real time. Not neat conclusions wrapped up with certainty, but messy data, competing interpretations, questions that multiply faster than answers, and researchers working to make sense of signals arriving from an object that formed in a place we'll never visit, around a star we may not even be able to identify. Stay informed, keep watching the skies, and remember that somewhere out there, roughly 269 million kilometers away as of December 19th, an icy visitor from interstellar space is continuing its journey, indifferent to our questions, unconcerned with our confusion, Following laws of physics that we're still working to fully understand, the universe doesn't owe us answers, but it keeps offering mysteries, and that's more than enough to keep looking up.